We have a new lecture packet now pertaining to test form material. It includes 4 topics: integration by parts, trig integrals, trig substitutions, and partial fraction decompositions. Some of these sections in the textbook are rather long, especially the one on the trig integrals. That may take a couple of class periods. The one pertaining to integration by parts is relatively a short section. We will cover all 4 topics, and as always, you have a lecture packet with the problems that we're going to cover in class. You also will be introduced to formula sheets that will be attached to your test so that you will know how to use the formulas and know where to find those on the sheet. One type of formula page that you would have would be like this very first page. These tables do not come into play until we go to the section on trig integrals. So we're going to have not only formulas, but we're going to have tables. The first topic that I'm going to introduce is integration by parts. That is the purpose of this video. The one section and just some basic information and maybe 1 or 2 basic examples. So, integration by parts. The reason we need something called integration by parts is when we have as our integrand a product of 2 functions called f times g, and we would like to solve and find that antiderivative, which you know is equal to y, and it's a family of functions. So whatever it would be, since this is an indefinite integral, you would remember to add a plus c. Methods from our past may not be able to be used to find the antiderivative for a product of f times g. With the new method of integration by parts, it may be possible. There is a formula for integration by parts, and I'm going to write down the formula, and then we're going to derive the formula. Usually I do not focus on the derivation of a formula or the proof of a formula, but I feel like the proof of this formula is very important to understanding integration by parts. First of all, let me list the formula before we start proving the formula. Again, this is the formula for the indefinite integral. Later, I will show you the formula for the definite integral. It reads, the antiderivative of u with respect to v is equal to u times v minus the antiderivative of v with respect to u. And you may say to yourself, where is f, where is g? You have u and v. In the proof of the formula, you will see how we start out with an integral that looks like this, a product of 2 functions as an integrand, and we will derive this formula in terms of variables u and v. So this is the proof. And I begin by saying, consider the antiderivative of little f times little g with respect to x. Step number 1. Let capital G of x be any antiderivative of little g of x, such that when you take the derivative of the antiderivative, you get little g back. I think we've discussed that before. That's a true theorem. If capital G is an antiderivative of little g, then when you take the derivative of the antiderivative, you get little g back. This says so there's your antiderivative, capital G, and our family of antiderivatives would be capital G plus C. when you go to take the derivative, obviously the derivative of the constant of integration is 0, you receive little g of x. So the derivative of the antiderivative is the original integrand. We discussed that at the beginning of the semester. Step number 2. Consider taking the derivative with respect to x of the following product, f times capital G. And we're going to use the product rule to find that derivative. So little f times capital G. The product rule says first function times the derivative of the second plus the second function times the derivative of the first. So we have f of x times g prime of x plus g of x times f prime of x. What I'm going to do, where you see capital G prime of x, I'm going to replace it with little g. Because we know, and I'll use a different color, that the two are equivalent. So little f times little g plus capital G times f prime of x. Now that we have step 2, we can go into step 3. So we have just proven that the derivative of little f times capital G is little f times little g plus capital G times the derivative of little f. Step 3 says, thus, what this means is, if we take the antiderivative of little f times little g plus we should get back, when we take the antiderivative, we should get, as a result, little f times capital G. So these two are related. If you take the derivative of little f times capital G, this is your result. And that means when you go to integrate little f times little g plus capital G times the derivative of little f, which we did here, we get our original little f times capital G. Sometimes people will maybe, to define this, if we actually put an integral symbol here and here and here, obviously if we do that, we would also want to add dx, excuse me for this, dx and dx to make it an integral and complete notation. But if you integrate both sides of that, then that is when you have that the antiderivative of little f times little g plus capital G times the derivative of little g, the antiderivative of that will get you back to what we started with, the product of two functions, little f times capital G. Now, with that being said, on the left-hand side, we can break this up into two separate indefinite integrals. There we go. So I separated the left-hand side into two separate indefinite integrals. Step 4, if you notice what we started with on the first page, we wanted to consider solving for this particular integral with the integrand being a product of little f times little g, and we want to consider solving for that. So here at step 4, which is based upon the steps above, steps 3 and 2 and 1, I am going to solve this last equation for the antiderivative of little f times little g, which means I'm going to subtract this antiderivative from each side of the equation. So the right-hand side of the equation is going to be little f times capital G minus the antiderivative of big G times the derivative of little f with respect to x. Therefore, we have somewhat of a formula now for solving for this particular type of integral with this product of two functions. And this is where we begin to introduce the variable u and the variable v so that you end up with the integration by parts formula. And that would be step 5, and then we would be able to go to our conclusion. So with step 5, you got to let some things happen. You let little u be little f of x, and you let lowercase v be capital G of x. Now, once you let those two things happen, you take the derivative of each. So what this means is the derivative of u with respect to x is equal to f prime of x. And if you cross multiply, du is equal to f prime of x dx. Very, very important. With this side, if I take the derivative of little v with respect to x, I get capital G prime of x. And if I cross multiply, dv is capital G prime of x dx. And capital G prime of x, back at step number 1, was proven to be little g. So I'm going to replace capital G prime of x with little g. And that means dv is equal to little g dx. And I'm going to put boxes around some very important items. Box, 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 and box. I call these the 4 parts of integration. Integration by parts, well, these are the parts. And then number 6 is going to give us our formula and tie everything together. So here we go. Here's the formula. And I'll show you how this is true. We are going to go in and substitute. So we said in the box that u is f of x. dv is g of x dx. Look at that. Neat. And that is going to be equal to u times v. So u times v, which is little f times big G, minus the antiderivative of v, which is big G, times du, which is f prime of x dx. And if you go back up to step number 4, is that not what we have? U dv, u times v, and then finally v excuse me, v and du. And I'm going to write that underneath. So u is little f, g of x dx is my dv in the formula. This little f is u, big G is v, big G is v, and then f prime of x dx is my du. And all I have to do is go back in, and I'll put my integral symbols. Oh, excuse me, the integral symbol goes there. And there's a minus there. So we have the formula. The antiderivative of u, dv, is equal to u times v minus the antiderivative of v with respect to u. So you can see 4 and 6 agree. And you may want to watch the video a couple of times, or better yet, I suggest as you watch the video, maybe you write down the steps yourself and make the connections. And you will definitely see how they derive the formula for integration by parts. Now, some basic examples, which brings us to a acronym that's very important, and it is called LIATE. L is logarithmic, I is inverse trig, A is algebraic, T is trigonometric, and E is exponential. The reason they give us this acronym is when we are presented with a problem like this, especially when we have two functions, we have to make our decision which one of the two functions will be u. And in order to make your decision on which one of the two functions would be u, you follow the acronym from top to bottom, where logarithmic comes first and exponential goes last. Now, if you have an integral that has just one function, then that one function by default is u. So with integration by parts, you always have to start with the first step, look at what you have, and decide what u should be according to the acronym list. Obviously, if it's one function, then that's your u, and that helps you to go and start the problem successfully. But when you've got a product of two, you have to let u be the first one that occurs in the list. And thus now I feel like we can go and we can look at an example together. I have these examples in the lecture, and I'll show these examples in the lecture. If you notice, I already have the final answer and I have the 4 parts of integration. I'm going to work the problem as if we don't see the answer and we don't see the 4 parts of integration. So I'm going to go back to the problem, and we have a product of two functions. The first function is f of x equals x, and the second function is g of x equals cosine x. Well, f of x equals x is algebraic. Cosine x obviously is a trig function. LIA, and you can also draw it that way, LIATE, the one that comes first is the algebraic function, f of x equals x, and then trig functions. So our first box will be u is equal to x. First box. Now here is how you decide what dv will be. Once you decide that u is x, here's your second box. dv is the rest of the integrand and what's left over. It's kind of like once you take this x out, cosine x dx is equal to dv. So these two things just happen by the acronym as part of the process. So dv is the rest of the integrand. Once you do that, your next box will depend on taking the derivative of u with respect to x, which in this case is 1, and then you want to cross multiply to receive du equals dx. There's my third part of integration. In this process, what we want to do is we want to solve for v. V is equal to the antiderivative of an understood 1 with respect to v. I think everybody knows that, just in general. I could say v plus c equals the antiderivative of 1 with respect to v. This means that we have and that simplifies to finding the antiderivative of cosine x. And that will give us our v, which is our fourth part of integration. And everyone should know what the antiderivative of cosine x should be, and it's sine x. Usually you would say plus c, but in the box you will not include the plus c. If you include the plus c, I will count off. Now that we have our 4 parts of integration, we can go through and show how we solve our initial problem. This is what I do. I write my problem, and then I take like a different color of pen. I just used orange, so I'll just use regular black ink. This left-hand side represents the antiderivative of u, dv. Correct? U is x, dv is cosine x dx. And then I want to write underneath in black uv minus the antiderivative of v du, because I want to fill into my integration by parts formula by looking at my boxes above. Remember, our box says that u is equal to x and dv, u times v. U is x and v is sine x, so this is going to be x times sine x minus the antiderivative of v, which is sine x, times du, and du equals dx. Now I am going to take a highlighter and highlight this in a box because this is really not part of your workflow. So I'm going to highlight it. I want you to know it's not part of what you should be showing me step by step. But if you want to include it like I do so that I'm not thrown off by the whole process, do something like this to set it apart. Final thing I have to do is integrate sine x, and that's negative cosine x, and then plus an overall c. And made a mistake here, that's times. So your final answer is x times sine x plus cosine x plus c for the very first problem. And before that, there was not a method that we could use to find the antiderivative of x times cosine x. We needed integration by parts to be able to solve for that. So that is problem number 1. You can verify it here. And then these are the 4 boxes. Problem number 2, or example number 2. We have the antiderivative of x times e to the x. This is the answer I will show you. And then here are the 4 boxes. I'm going to pretend like we don't have any of that, and we're going to start from the very beginning. And I'm trying to solve this by integration by parts. So you have a product of 2 functions. Little f of x is x, and it's algebraic. Little g of x is e to the x, and it's exponential. And you look at your acronym, which builds all the way up from logarithmic to exponential. Once again, algebraic comes first. So your first box, u is x. Second box, dv, is the rest of that integrand, whatever's left over. And that's e to the x dx. These 2 boxes then determine du, and this box obviously determines v. Du with respect to x equals 1, du equals dx, box. Here, once again, v is equal to the antiderivative of an understood 1 with respect to v, which in this case, dv is e to the x dx. And we know that the antiderivative e to the x is e to the x plus c, but do not include plus c in your box. And then we're ready to substitute into the formula. So I start with my original problem. And with a different color, I just want you to see that x is u, and then this is dv. And I have uv minus the antiderivative v du. Different color. So I can plug in u times v is going to be x e to the x minus the antiderivative of v, which is e to the x, du, which is just dx, according to your box. Final answer is very simple, x e to the x minus e to the x plus c. And that was problem number 2. Problem number 3, you can see, is only one function, so that automatically has to be our u. You see the answer, you see the 4 boxes, but we'll start from the beginning and prove that answer in those 4 boxes. We have one function, therefore u is natural log of x. There's box 1. dv is the rest of the integrand, so that all that's left there is dx. The derivative of u with respect to x is equal to 1 over x, so du is 1 over x dx. That's your third box. When you want to find v, you take the antiderivative of an understood 1 with respect to v, which in this case, that's the antiderivative of an understood 1 with respect to dx. And therefore, v is equal to x plus c. But do not put plus c in the box. Now we're ready to substitute into our formula. Original problem. This side is my u dv. So u is natural log of x, dv is equal to dx, as in the boxes above. U times v, or we can also say v times x, or excuse me, u times v or v times u. You have u as natural log x and v is x. You're not going to see it written as natural log of x times x unless you have parentheses around it. You would want to write it actually as v times u. It looks better. But if you put natural log of x first, you will need parentheses around natural log of x times parentheses around your x. So I prefer to write it as v times u because multiplication is commutative, minus the antiderivative of v, which is x, times du, which is 1 over x dx. So I'm just replacing v with x and du with 1 over x dx. Final answer. I believe you know that the integrand here becomes 1. And the antiderivative of that understood 1 now is just x. And that concludes this lecture presentation on some basic integration by parts. Again, this is the very basic information. There are times when you have to go over integration by parts more than once. Sometimes you have to do it twice. And also, there is a time when you will have to do this. And this will go from A to B, A to B, A to B. And you will be working with definite integrals there, but you can still use integration by parts. Stay tuned because I plan to give you some more complicated examples of integration by parts in your lecture. Those would be the types of problems that I would include on the test. These are very